Welcome to this explainer. Today, we're going to decode the secret language of machines to keep our industrial operations running smoothly. If you've ever stepped foot on a bustling plant floor, you already know it is an incredibly loud, chaotic environment. But right beneath all that noise, there's a highly specific, microscopic conversation happening every single second. Our source material, specifically Chapter 20 of the IT-204 textbook, frames this perfectly. It says, vibration is the language of machines. Machines are always trying to tell us how they feel. Honestly, it sounds a bit poetic, doesn't it? But it's entirely grounded in hardcore physics. We're going to explore how tuning into this unique language can drastically extend a machine's life, save a ton of money, and completely prevent catastrophic failures. Here's our roadmap for today. We'll be covering the language of machines, why we monitor, measurement pillars, proximity transducers, and finally, mitigating failure. We're going to shift smoothly from mechanical physics right into the electrical engineering used to detect it. Okay, Section 1, the language of machines, understanding the basics. Let's get right to it. So what actually is vibration? At its core, it's just a machine oscillating. It's that back and forth movement of a machine component around a resting reference position. And when we want to know how fast this back and forth movement is happening, well, we're talking about frequency. The frequency tells us the exact number of complete motion cycles that happen in just 1 second, which we measure in hertz. Now, a machine doesn't just vibrate at random, right? It's strictly controlled by 3 physical traits: its mass, its stiffness, and its damping. When these are acted upon by your typical industrial issues, say repeating centrifugal forces, some physical looseness in the components, or even structural resonance, that is exactly when the machine begins to speak through vibration. Moving on to Section 2, why we monitor vibration, the high stakes. You know, almost every moving part, pumps, motors, belts, fans, can literally shake itself apart if we aren't paying attention. The consequences of just ignoring vibration are severe. We're talking about critical machine damage, incredibly high power consumption, and major quality problems. And worse than that, it creates really dangerous occupational hazards. I mean, prolonged exposure to vibrating equipment can actually cause nerve and circulatory damage for workers. And this leads us to a huge shift in how modern plants operate. Historically, we relied on preventive maintenance that's purely time-based. Basically, swapping parts every few months whether they need it or not. It's essentially blindly guessing, which still leaves plants vulnerable to highly costly, unexpected outages. Today, though, we use predictive maintenance. This is condition-based. By permanently installing sensors to actively listen to the machine in real time, industrial plants only fix what's actually breaking. It saves vast amounts of money and completely prevents those dangerous, unplanned shutdowns. Let's jump to Section 3, the 3 pillars of measurement and axes. To translate this mechanical language into data we can actually use, think of measuring machine health like measuring a road trip in your car. Our first pillar is displacement. In a car, that's total distance traveled in miles. For a machine, it's the tiny distance the metal actually moves, measured in microscopic units like microns or mils. Our second pillar is velocity, which is how fast that displacement changes. In a car, that's mph. For a machine, we measure it in millimeters per second. And finally, acceleration. Just like the g-force you feel when you slam on the gas pedal, we measure the machine's time rate of change of velocity, usually utilizing the acceleration of gravity, or just g. Okay, so we have our units. Now, where do we actually look? When we inspect a physical machine shaft, data is systematically collected across 3 primary axes: the vertical direction, the horizontal direction, and the axial direction. The specific direction of the shake is a massive clue. It tells us exactly what's failing inside. Here's a great comparison of the 2 most critical types of movement. On the left, we've got radial vibration. This is a force pushing outward from the center of the shaft. So if a motor has a heavy spot or a warped fan blade pulls outward as it spins, you get radial vibration. It is absolutely our best indicator of rotor imbalance. Now, on the right, we have axial or thrust vibration. This is motion running parallel to the shaft's center line. When you see axial vibration, it's almost a guarantee that you're looking at a shaft misalignment between 2 connected machines. Section 4, the proximity transducer system, or proximeter. So this brings up a fascinating engineering challenge. How do we actually capture these microscopic displacement movements? We're talking just a few thousandths of an inch in a loud, chaotic industrial environment. We use a proximity transducer system, or proximeter. Think of it as a mechanical stethoscope. It uses this brilliant 4-step process.
First, an oscillator circuit generates a radio frequency, or RF signal. Second, the rotating conductive metal of the machine shaft enters this RF field. Third, this interference causes eddy currents to flow right on the surface of the shaft. And finally, a demodulator circuit extracts the raw data. To get the best frequency spectrum capture, these sensors are usually stud-mounted directly on a flat, clean surface of the machine casing. The really cool part is how the physical movement actually alters the amplitude of that RF signal. As the vibrating shaft gets closer to the probe, closing the gap, the eddy current flow hits its maximum, which drops the RF amplitude down to a minimum. Then, when the shaft vibrates away, the gap widens, and the RF amplitude shoots back up. So the changing gap is literally modulating the signal. And here is the final beautiful translation. That raw RF signal looks pretty chaotic, but the demodulator steps in and splits it into two distinct components. It gives us a constant DC voltage, which represents the static gap or position of the shaft. Simultaneously, it outputs an AC sine wave, where the peak-to-peak voltage represents the dynamic vibration. These systems are incredibly fast, too, boasting frequency responses all the way up to 10,000 Hz.
And finally, Section 5, Mitigating Machine Failure.
Okay, the data is flowing. Once these sensors trigger our two-stage warning and trip alarms, which automatically shut down a failing machine before it destroys itself, how do we actually cure the problem? Well, we rely on two main mechanical techniques. The first is machine balancing. Remember that heavy spot causing radial vibration? Balancing just means adding or subtracting weights to make the effective mass perfectly equal all the way around the rotating axis. The second technique is machine alignment. This tackles that axial vibration by precisely adjusting the machines to ensure absolute centerline coincidence across all the rotating parts. As we wrap up this explainer, I really hope you leave with a fresh perspective on the physics hiding inside our industrial world. Next time you're standing next to a humming motor, a pumping engine, or honestly, even just your washing machine at home, ask yourself, what is it trying to tell you, and are you equipped to listen? Thanks for joining me, and keep your ears tuned to the language of machines.